Our first panel this morning is going to be on the importance of technology and innovation for our economic future. The panel moderator is a fellow named Joe Parrish. I've had the privilege of working with Joe for a while now. Joe is the NASA Deputy Chief Technologist. He comes to NASA headquarters from the Jet Propulsion Lab in Pasadena, California. And he also, before coming to NASA, worked in the private sector and has at least one payload aboard the International Space Station. I also know it's a privilege for Joe to be here today because I like airplanes. Joe loves airplanes. Joe is an accomplished private pilot. He flies an airplane that's very odd looking. It has a propeller in the back of it. And I've been to airports with Joe. He's a kid in the candy shop, and I know that the Museum of Flight is an awesome place to visit. Again, the exhibits here are amazing. They've got the history of flight from the beginning to the present to the future, and it's just a great place to be having our future forum. And with that, I'll turn it over to Joe Parrish.
Great, thanks very much, David. Well, it is wonderful to be here this morning with you all. Just as Lori gave her shout out to Bill Nye, I'd like to give a shout out to my twin brother, Jerry, who is sitting in the front row there. Jerry actually is the person who built that funny-looking plane that David mentioned, and he built that plane here in Seattle, right across the runway from where we are now, in a little hangar over on the other side of Boeing Field. So thrill for me to have my brother here. He built a very innovative airplane, and then we share that plane now, and it helps to fuel my enthusiasm for flight and moving on into all of aerospace and the space program. So thanks for Jerry for being here. Also wanted to thank Doug King and the rest of the staff at the Museum of Flight for their incredibly warm welcome to us and to allow us to talk today about innovation and technology. And we have a terrific panel here. My colleagues, Bob Pierce from NASA, Christy Morganson from the University of Washington, Roger Myers from Aerojet, and Ed Lazowska from University of Washington have a fantastic plethora of experiences and ideas about innovation that they're going to be sharing with us this morning. The way we thought we would construct this next little bit more than an hour that we'll be spending talking about innovation is each of us, we're going to talk a little bit about innovation from our own perspectives, and then we had a sort of overarching question that we posed to each other to talk about, and those are what are the major technology challenges that we're facing now? How do we see our technological future evolving, and where do we think we're going to be in 20 years in addressing those technology challenges, and what role might innovation play in that? So you'll hear us talk a little bit about our own perspectives on innovation, and then we'll talk and address that particular question. The other thing that I was going to do is rather than hit you with a barrage of introductions of my very accomplished colleagues, I was going to do them sort of one at a time. So I was going to make a couple of short remarks first, and then introduce Bob, and then we'll move ourselves across the row. So thanks very much again, and really looking forward to this discussion and looking forward to having a dialogue with you. So I hope that as we talk, you'll be thinking about questions that you'd like to ask us, and we'll take them and really start to engage and think about innovation and technology. So a couple of thoughts. And I've been thinking a little bit about, what is the meaning and what is the significance of technology and innovation? And I have a somewhat unconventional definition of what innovation actually is. I think that innovation is the constructive rejection of the status quo. And what I mean when I say the constructive rejection of the status quo is if you're satisfied, and Lori started to talk about this a little bit in her remarks, if you're satisfied with the status quo, you're not an innovator. Right? You're okay with your television set being almost 2 feet deep and weighing 200 pounds and carving big holes in your shag carpeting in your living room. If you're satisfied with when a question comes up in your conversation to walk over to the Encyclopedia Britannica and try to find which of those 30 volumes has the answer for you and bring that back to the discussion, then you're not an innovator. You're okay with the status quo. And thankfully, we as a nation, we're not satisfied with the status quo. We never are, and we always want more. We want to have the ability to pull from our pockets this little gadget that not only allows us to talk to anyone on the planet practically, to answer practically any question that one might pose. Now we don't even have to type in that question. We can talk to that little gadget. Imagine what that means. Imagine how incomprehensible that is to somebody 100 years ago, 50 years ago, even 25 years ago to be able to do that. It's wonderful to be here in Seattle, one of really the hotbeds of innovation in our nation, and that is not a new thing. Starting, with the innovations that Boeing has made to make the United States the world leader in aviation, with Microsoft, and even with Starbucks. I personally think that the drive-through Starbucks is the pinnacle of human achievement, and I'm not sure that we can really go much further than that. So thanks to Seattle for fostering innovation for the rest of us in the country and in the world. I wanted to talk a little bit about the fact that investments, you all are taxpayers, and you are investing in our future with your tax dollars. And it's easy for some to ask the question. Unfortunately, none of the people who ask this question are sitting in this audience because you guys already get the answer. But some people ask, why are we taking these dollars? Why are we taking these precious tax dollars and firing them off into space? And to that, I respond, you know what? We're not actually packaging up a bunch of dollar bills into the nose cone of a rocket and firing it onto Mars to be spent by Martians on that planet. And we're not doing that, actually. We're actually spending that money on planet Earth, and in the process of developing the systems that we do send to Mars and to Jupiter and to Saturn and beyond, we're enabling things here on planet Earth. We're spending that money on Earth. We're creating high technology jobs that in turn inspire new ideas and create new ecosystems of supporting companies. Think of all the companies that support Boeing as tier providers. Think of all the companies that are going to support this burgeoning commercial launch industry that NASA is helping to kick off. So what is it about NASA, and how does innovation actually happen at NASA? As Lori mentioned in her opening remarks, this is kind of a transformational period in NASA. We're ending the Space Shuttle program, and we're embarking on an ambitious new plan to send humans to explore beyond Earth orbit, to the moon, to asteroids, and ultimately onto Mars. In order to do that, we're asking our people at NASA to create incredible things. And in order to create these incredible innovations, we believe that we need to create an environment of innovation within NASA to inspire those innovative products. So we do that in a variety of ways. Number one, we are really keeping our eyes open for broader societal benefits to the things that we develop. Now, you all have heard of things that we call spin-offs, where we'll develop a technology at NASA. We'll recognize that that technology has applications beyond just the NASA ecosystem, and we look for ways to apply those technologies in the commercial sector or to help people all over the planet. And we're actually increasing our emphasis on our view toward broader societal benefits. We've also chosen to take unique new approaches to engaging with the most innovative thinkers in the country and around the world by engaging them in ways that are not traditional. And the traditional ways that I'm referring to are like contracts that NASA would issue to an aerospace firm or a grant that they would make. We're looking at new ways of doing business, and one of the ways that we have chosen to do this is through prizes and challenges. And one of the wonderful things that we've just done this last year is NASA created a challenge called the Green Flight Challenge that was a prize for the highest performing small aircraft, and we were asking for this to basically be a Prius in the sky, to get the equivalent fuel economy to what a Prius car gets on the ground. We wanted 200 passenger miles per gallon from this aircraft, and this year in California, we actually had two aircraft. The one that finished in second place got 385 passenger miles per gallon, and the winner got 413 passenger miles per gallon from an airplane. That is astonishing, and it's nothing that we could have ever imagined in the past, and it was through competition. We issued a prize to the winner, and the competitors sunk much, much more than NASA gave out in that prize to develop the aircraft that competed in the competition. So We inspired new things, new technologies, new innovations, and we went about it in a way that was vastly different than the way that NASA has done things in the past. And we see more and more of that coming in the future. Let me close my comments a little bit in discussing today's technology challenges. One thing that strikes me is that technology goes at a pace that we can't predict. Unfortunately, it would be wonderful if we could predict these things, but we can't. And I'm struck by things that have gone at a much faster pace than we could have ever imagined. Think of cell phones and computers as things that we could have never imagined, how quickly they evolved. Technologies associated with transportation and the environment are evolving quickly. We're looking to having wind power, solar power, other methods of non-polluting power, and the technology that's necessary to make those cost-effective with the higher polluting approaches, those are evolving on a very rapid and increasing pace. And then, let's be honest. I think that the evolution, the pace of technology development in some segments of the aerospace sector have actually gone slower than we imagined, right? Who would have thought in July of 1969 that we would be 42 years later and not have gone any farther than the moon? I think people who were watching the moon landing on that day would be very disappointed that fast forward 40 years and that's really as far as we've gone. So we have more work to do, and we think at NASA very hard about this problem and think about how we can accelerate the pace so that the pace that we make progress in aerospace applications for both aeronautics and space, how do we bring that pace up to the pace that we've seen in the computer, consumer products industry, energy, and transportation industries. So there's a variety of things in play right now, and it's a very, very exciting time to be alive and be participating. So those are just some thoughts that I wanted to kick open the discussion with. And so with that thought, I'd like to introduce my colleague, Mr. Robert Pierce. Bob is our vision guy in aeronautics. He is the director for strategy, architecture, and analysis in the Aeronautics Research Mission Directorate, which is one of 3 directorates that we have at NASA, the other 2 being science and human exploration and operations. Bob plans the strategy, the look forward for what we're doing in aeronautics, trying to make aviation more fuel efficient, more more lower noise capabilities, increasing our ability to manage traffic as we get more populated in the United States and air traffic starts to increase, and how to do that in a safe and effective manner. That's Bob's job. And he's a fascinating guy. I asked actually all of our panelists to give me a little sort of personal tidbit about themselves to make this a little bit more human, because the resumes are all incredible. Bob is a runner and actually just did his first half marathon this year. And so congratulations to Bob on 13 tough miles. And he's going to talk with us a little bit about innovation in aeronautics and talk a little bit more about how he views the future as we move forward. So please welcome Bob Pierce.
Thank you, Joe. And it's a real pleasure and a real honor to be here at the Museum of Flight, and I certainly plan on taking a walk around and really enjoying the exhibits after this is completed. And actually want to ask you guys to do something as well on a walk that we often take. I want you to do something very specific. So the next time you walk onto an airplane, on the next trip you're going to take, I want you to look around a little bit. And so first, when you go in and take a look to the left and you look into the cockpit and you see those glass displays, a lot of those originally, the functionality in those displays originally pioneered by NASA. If you were able to look behind those glass displays at the digital flight controls that many airplanes have, the nervous system in an airplane, that was originally pioneered by NASA. If you actually look at the pilots interacting together, that crew resource management, as we call it, again, something that NASA pioneered, those human factors in order to improve safety. And then when you turn and you go down into the airplane and you see all those really tight, cramped, uncomfortable seats, yeah, that's not NASA. That's not NASA. Okay. But if you kind of peered over those seats out the window and onto the wing, and if you looked at the cross section of that wing, most of the modern wings are supercritical airfoils, again, pioneered by NASA. You look at the winglets that the little wings that stick up at the end of the wing. that many airplanes have, again, pioneered by NASA. The overall shape of the airplane, called the area rule. If you were able to look into the engine, the low emission combustors that efficiently burn the fuel, but emit as few of the bad emissions as possible. If you look at the lightweight, high temperature alloys that are in that engine and allow the core of the engine to be as small as possible, so we get the largest bypass, so the fan can be push as much air as possible, make the engine as efficient as possible. Again, NASA, the shape of many of the components inside the engine to allow a really optimal balance between the efficiency of that engine and the noise characteristics. Again, NASA. If you look at the latest designs, when I drove in, you see the 787 parked out there, just a magnificent Boeing airplane, and half of that airplane, 50% of that airplane is composite materials. NASA spent 30 years working through all of the issues associated with composite materials so that we could safely apply them in a very efficient way. If you look at the engine, at the back of that engine, you see this kind of scalloped shape. It's a chevron nozzle. It helps in the mixing of the jet flow to reduce the overall jet noise that comes off the airplane. And all of that innovation, we build that into tools, into CFD tools, into structural design tools and so forth, and all of those are available to the industry, and those tools get used to build those modern airplanes. So when you walk, and in fact, this is a Boeing term, but when Boeing talks about it, they say it's the NASA DNA that's in every airplane. And so I walked through a commercial airplane, but I could do the same thing for a military airplane. You could do the same thing for a general aviation airplane, for helicopters and so forth. The DNA of all of those, everything that flies, started at NASA. And so we're very proud of that, and we're really proud of that tradition. Let me talk just a minute about why do we care? Why is that so important? Why is this an economic engine? And if you look at aviation, it is absolutely the safest, highest speed, global mobility provider. It is what we use, and there's no substitute. Today, domestically, if you look at an annual basis, we have 600 million passengers that fly on 20 million flights, totaling about 600 billion revenue passenger miles annually. We do all that flying for 1/2% of GDP. It is an efficient industry. But if you look at that, and if you look at what's the impact on our economy, all of getting the people where they need to go, the goods where they need to go, the industries that absolutely require that capability, and now the impact, the benefit is over 5% of GDP. So it's a big multiplier. It's a big impact. And I think if you look at aviation, if you look at those industries, and especially if you look at the manufacturing, let's just look at manufacturing for a second. It's incredible that now just commercial transport. I'm not all of aviation. Commercial transport. If you take a 20-year view of the commercial industry, $4 trillion market. It's a global market. Huge growth in the Asia-Pacific region and so forth. And so we enjoy, because of Boeing and because of the thousands of companies that contribute to those airplanes, we enjoy a $40 billion annual balance of trade in airplanes. And of course, Boeing is having record sales, and everybody around here, I'm sure, knows that. You look at the newspapers, the 777, the 737 MAX, and so forth. You look at 737 MAX. Why is that so important? Why is that? Because if you look, even though the airlines provide so much benefit, not everything is good news, right? The cost of fuel has risen by a factor of 6 in the last 20 years as a function of the cost that the airlines pay. It's gone from about a quarter. They used to pay about a quarter of their total cost for fuel. Now they're a half. Now, that's really tough to manage an increase like that, but you can also see fuel went up by a factor of 6, but that only went up by a factor of 2. And the reason is those airplanes have gotten a lot more efficient. And so the need for new airplanes, the need to continue to push that envelope is going to continue. But $4 trillion market attracts attention. So now you have Embraer from Brazil, you have Bombardier from Canada that have pioneered in the regional jet market. Now they want to get into the larger scale jets because they see that market and they see that there's an opportunity there. Obviously, China and the COMAC is coming along as well. So there's a lot of competition coming, but this is exactly the type of industry that the U.S. needs to be successful in. The scale, the market, as I just talked about, but this drives manufacturing and drives employment. These are not, you know, there's some industries in IT and other places where you get a lot of market, but it doesn't employ a lot of people. This employs a lot of people. You look at the scope of technology. It needs every bit of technology from every corner that you can imagine. But most importantly, I'll get to one of Joe's points. What are the tech challenges? One of the really critical things, one of the things Boeing does well, but we as a nation need to do better, is integration. It takes incredible software, incredible hardware, and the people. Sometimes we forget that the person that operates the airplane, the person that operates the air transportation system is part of that system, and all three need to work together flawlessly to make sure it's robust, to make sure it's resilient, to make sure it's perfectly safe. This industry has to be safe. So it puts requirements that perhaps other industries don't always put on it. So these so-called human cyber-physical systems, the integration around that is, I think, one of the premier technical challenges of the 21st century. It is what we as a nation have to be the best at. We've got to make these things work from the beginning, work right, make sure they're robust, make sure they're safe, and that is going to be the high ground for, I think, for the next several decades. Okay, let's take a quick look at the future. So when NASA looks at this, of course, we're not looking at current vehicles. We're trying to look at a generation or two. We're trying to look at where things are going. So we put things in sort of generational terms. When we look out a couple generations, we're looking at orders of magnitude improvement in noise and efficiencies and so forth. We want to make big strides, okay? And the questions, and so there's a lot of technologies that go into trying to make those things happen. And I have numbers, in the interest of time, I won't go through the kind of numbers we're looking at, but we look at noise, we look at emissions, we look at efficiencies and so forth, trying to make those much better. So some of the things we're looking at is, when does the current configurations, the tube and wings that we're so used to looking at on the runway and so used to getting onto, when does that have to change because we can't eke any more efficiency out of that kind of configuration? So we're looking today at hybrid wing bodies, kind of these bat wing type airplanes where the wings sort of wrap back on themselves in order to get very high aspect ratios. Strut brace wings that are very long, and we kind of use braces to make sure that those very long wings can operate at the kinds of Mach numbers and operating conditions we're looking at. So that's another technical challenge, is how do you make that transition from today's very mature and understood configuration to a configuration that's very different, but that you have to go to if you're going to continue to make the kind of strides we want to make. So that's another big technical challenge. And propulsion is the same. At some point, we're looking at hybrid electric propulsion, distributed electric propulsion, and so forth. So another big technical challenge for the future. Let's just broaden the aperture a little bit and look beyond just commercial air transportation. Let's look at UAS, so unmanned aircraft systems. The military has pioneered these systems, and they provide the kinds of surveillance and other missions that the military needs. But today they can't fly in the airspace system. They can't fly except on a special exception basis. They can't fly when in the same airspace that pilot aircraft fly. NASA is taking that challenge on, looking at the issues with respect to the pilot. The pilot sits on the ground for the UAS, at least currently. At some point, maybe there won't be a pilot. But what's taking that challenge on, looking at the issues with respect to the pilot. Didn't I just say that? Sits on the ground for the UAS, at least currently. At some point, maybe there won't be a pilot. Okay. Whoa. Didn't I just say that? Okay, we're having technical difficulties.
Speaking of technology,
yeah. Is anybody? Yeah, something. Yeah.
Please please bear with us.
Nothing can go wrong with these drone aircraft, don't you worry.
That's why they're not actually flying.
Okay.
Yeah, exactly.
Sounds like we're back online. We just lost control of the UAS for just a moment. we now have it back. NASA's going to fix that problem. Sounds like we're back online.
We've still got a
UAS for just a moment. We now
I think we're in time dilation.
NASA's going to fix it.
I've seen this episode.
Yeah.
Are we,
Do you dare?
Try again.
Derek, are we back? Okay. So NASA's working on the problems of actually integrating the UAS into the national airspace. So the separation assurance requirements, we have to make sure they don't run into other airplanes. We have to make sure the pilots actually have situational awareness. We have to know how to certify these things. So NASA is working on that. But you can imagine the kinds of, in some ways it's hard to imagine really what all the applications are. Some of the initial applications for search and rescue, for firefighting, for law enforcement, and so forth. But if you think long term, think about what's coming. Joe talked about innovation in the economy. Imagine when already if you look at the way packages are distributed, the whole cargo industry, UPS and FedEx operate a very distributed small aircraft network. Those all require pilots. Those all have significant cost. If you could take the pilot station out, if you could put more packages into one of those small airplanes, you could get better distribution. And then, look at innovations outside of aviation. Look at 3D printing, right? So 3D printing, you start to build up parts and products. You print them on these 3D printers. It just lays the materials out just as in a normal printer, except now you get a 3D object. This could lead to a revolution in the distribution of manufacturing capabilities on a geographic basis. And wouldn't it be great to have UASs that could support that kind of a distributed manufacturing base? Look at the future of energy when energy becomes much more distributed part of the infrastructure. Millions of wind turbines and millions of rooftop solar panels. What if you had UASs that could robotically do the maintenance on these millions of distributed systems that provide energy for us? So you can think of all those possibilities. And I'll just add one last piece. I didn't mention, but one of the issues we've got in the air transportation system is we're losing the short haul part of it because of if you look at more or less than 500 miles, it's dropping off precipitously. People don't use air transportation as much in that domain, partly because of the hassle of getting through the airport and so forth. But imagine, now think of the airplanes that Joe just talked about, that were flown in the Green Aviation Challenge. Here's a small airplane, can do twice what a Prius can do, 4 times the energy efficiency of a 787, as a matter of fact. Now, if you could get these small aircraft to operate into and out of small airports and provide that short haul capability, it'd be a real step forward. What's one of the big impediments? One of the big impediments is you'd have to either hire a pilot, really expensive, or you'd have to be a pilot, and so people like Joe would love that. But lots of folks don't want to go through the expense and the learning curve of being a pilot. Well, once we get the learning on the UAS, once we get more autonomy and automation, maybe these things don't have to be piloted. Maybe we can have the automation piloted. And so I know what you're all thinking, that when you land, you're not going to get the pithy joke from the pilot, but we're going to get there. We are going to get there. It's going to be an acceptable part of how we do transportation, both on the ground and in the air. Autonomy is coming. So I think there's a bright future for aviation, a lot of innovation left to be done, and NASA plans to be out in the forefront of that. So thank you very much, and I look forward to taking your questions.
Great. Thanks very much, Bob. You raised so many fascinating points in your talk, and I think that one of the most intriguing ones has to do with the way that humans and machines work with each other, and how do we best affect control over these devices. And that's why it's so wonderful to have Dr. Christy Morganson following Bob's comments with her own. Christy her specialty is, in fact, guidance, navigation, and control, control of vehicles, human and autonomous systems, and this is her expertise area, and she is particularly well versed in the area of underwater vehicles, and is going to talk probably about underwater vehicles and make a transition into aeronautical and space systems also in the course of that discussion. So if you need help making your robot swim straight, then Christy is the person for you. So thanks very much for Christy for being here, and look forward to your comments.
All right, well, thank you for inviting me to be here. So actually, I wasn't going to target my comments specifically at underwater vehicles, but I'm happy to answer any questions along those lines if people have them. And just as a point of fact, Bob and I did not compare notes ahead of time, but a number of my points are actually directly in line with his. So what I wanted to do first was just say a few things about autonomous systems. I think that a lot of the future of technology is going to lie directly in line with autonomous systems and already does. Probably in ways that are somewhat obvious in some senses to most people, but in other cases, you actually work with them every day and probably don't really think of them as autonomous systems. So some of just the big impact with them, they're meant to be transformational in human perception and access, what we can see and what we can do. So some of the big areas where they come into play, emergency response, and some of these have already been mentioned. So emergency response, so something like the nuclear reactor, disaster over in Japan, the oil rig, failure in the Gulf, medical robotics, environmental monitoring, so tracking fires and things like that, weather prediction, monitoring the ocean. That's actually where a bunch of my and many people's underwater vehicle applications come into play. Exploration, so space exploration, exploration around the planet, exploration inside of the human beings, and of course military action. So different kinds of autonomous systems that come up. So there's the vehicle side of things, and on that scale we have vehicles that range from tethered, so things that went down and explored the Titanic and go down and explore many other things underwater in space. That allows you to have access to power, unlimited communication, data transfer, things like that, and access to an operator directly. All the way to things that are completely untethered. So that would be something like your rover on Mars or these aerial vehicles, although sometimes you can tether some of them if you want to be a hobbyist and operate them without a COA. We can't do that at the university unless they're tethered. There's differences between whether they're fully autonomous, so they don't have anybody directly operating them, to whether there's a remote control device directly connected and there's a pilot running the vehicle. And often the pilot, particularly in like emergency response situations, they're actually backed up by 2 or 3 other people. So one of our big challenges right now is that a single autonomous vehicle may require anywhere from 2 to 5 or more people to make it fully operational and safe according to current standards. We're looking at situations where we have either single autonomous vehicles, single autonomous systems, all the way up to groups of them, where we're trying to expand the capabilities, and again, all kinds of different regimes with them. So some of our key technological challenges with these systems, the limited power. So again, if you don't have a tether to the vehicle, you have to work with whatever's on board the vehicle. So you have to have effective battery capabilities. Some of the appeal of the underwater gliders that I work with is they have a battery pack on board that allows them to operate for 6 to 9 months with no servicing, depending on the particular battery. How do you deal with this human and autonomy integration? So depending on what kind of regime you're working in, you might be able to drive a vehicle directly and have a remote operated situation, or if you have the rover out on Mars, it takes minutes just to even send a signal out to them, much less get data back. And over that kind of a channel, you're not sending a lot of information very quickly. Dealing with the actual interface between the human and an autonomous system, where I'm going to generically say that autonomous system might be something like a prosthetic device. There's a lot of work being done right now trying to further human augmentation in the sense of not trying to necessarily make the Borg from Star Trek, but trying to come up with better prosthetic devices for, say, people who've lost limbs or have medical conditions that prevent them from using their limbs. So there's all kinds of things that come up there: trust between the devices, security of wireless transmission of information, how are the devices perceived by people, safety, a number of things along the lines there, and dealing with the data transfer. So some of the key enablers, I actually wanted to mention some of these because I think these are key things. I think getting the general population involved is like historically a huge impact on making progress. One point I really wanted to make is what we often see or market as games and toys are in fact the steps to technological advances. I mean, this goes all the way down to, babies. I have a 1-year-old and you can watch him playing with blocks and he's figuring out how to manipulate the world around him. So what for him is a game is actually how he's gonna, I have no idea what he's going to build. I'm a little scared about that actually. But things like 3D printing, which may not be a phrase that's familiar to everyone, but the maker technology, so there are these devices where you can print, as Bob mentioned, a mechanism. You can also print cookie dough with them and bake cookies with your initials on the inside for a very low cost. So devices like that, getting them out to the general population and letting the population sort of drive where they go and how they're developed, that generally leads to low cost, high efficiency kinds of situations. Crowdsourcing, the movie industry, I would say that in 20 years, this is something we were targeted to sort of look at. What do we think might be happening? I think that James Cameron's vision of Avatar, while we might not do that specific kind of application of an actual genetically built second person, I think a lot of the things that you saw in that kind of movie are things that we will be seeing much more integrated into society in 20 years. So I think I'll leave it at that.
Thanks so much, Christy. I neglected to fill in the human element for Christy, although she's alluded to some of them with the 1-year-old, which must dominate your life. Christy's also an outdoor enthusiast, scuba diver, bicyclist, and mountain climber who's climbed Mount Kilimanjaro. So very, very impressive.
Although I have to admit, I didn't make it to the top of Kilimanjaro. I got altitude sickness the last day. So.
Okay.
I got to 16,000 feet.
That's pretty impressive. We have oxygen on when we're above 12,000 in the airplane, so that's terrific. Okay, so let's move on, and I'd like to introduce Dr. Roger Myers. He is the Executive Director for Electric Propulsion and Integrated Systems at Aerojet, which is a company that develops propulsion systems, and Roger will likely talk about this for many of NASA's missions, both human and robotic. Roger is also a forward thinker and has been responsible for strategic planning, development, and production of next-generation chemical and electric propulsion systems. Electric propulsion, for those of you who don't know, is sort of one of the next breakthrough technology areas for planetary exploration missions, and Roger is expert in that. He has a long history in research with NASA and in academia at Princeton. He and his wife live in Woodinville, which is wine country here in Seattle, a fascinating place where they enjoy bird watching as their in interaction with the outdoors. So please welcome Roger, and really look forward to your comments on propulsion technologies and innovation and where we're going in that area.
So good morning. So it's really nice to be here. It was a pleasure to participate yesterday in the opening of the Charles Simonyi New Space Gallery. So as Joe said, I was asked to comment on some of the transportation technologies. And I call it transportation as opposed to propulsion because it's not just about the rockets. It's also about the vehicles that are required to do this, to do the missions. And so in addition to talking about the technologies, I want to talk a little bit about some programmatic challenges that we actually face. What are the issues that we're really facing today? But I'll start with technology. So we heard today from Lori Garver about the dramatic cost reductions that are necessary in space transportation. We heard about the big rockets and how expensive they are. And if we're going to explore deep space, we have to get the cost down if we want to go beyond low Earth orbit. And essentially, it's just saying that the cost of developing, building, operating, and maintaining the launch vehicles and infrastructure required for those launch vehicles, as well as all of the deep space systems, the habitats, the landers, the ascent vehicles, and all the exploration equipment, within the budgets that we currently have is going to really have to change. We have to change our paradigm in the way that we do deep space exploration. And that's not rocket science as much as I'd like it to be. It's really just basic physics and economics. We don't have the money to do all of the big rockets that we would really like to do. And so we need to think about doing deep space exploration differently. The reason that it takes so many of those big rockets is energy. Going beyond low Earth orbit takes a lot of energy. There's a quote by a science fiction author that if you get to low Earth orbit, you're halfway to anywhere in the solar system. That's only true if you don't want to land and you don't want to come home. So if you want to come home, if you want to do something there and you want to come home, it drops it to about a quarter or thereabouts of the energy. The energy going to low Earth orbit is only about a quarter of the total energy required to do those missions. So if we want to go do something cool on the surface of Mars, we have to invest in the in-space elements. It's a requirement. You know, much as we make progress in our launch vehicles, and reducing the cost of the launch vehicles, we have to invest in deep space. So the reason for that is that today's propulsion systems, the in-space, what's available for in-space propulsion, are pretty inefficient. They're not very high performance, and that means that you have to carry a huge amount of fuel. You have to launch a tremendous amount of propellant to get beyond low Earth orbit. And that takes big, expensive, unique rockets to do that. And we have to change that paradigm. So if we're going to explore deep space, we need a balanced set of investments in both the launch architecture, the way that we launch people and cargo, and also we need a parallel set of investments in deep space transportation system technologies, deep space transportation architectures. As we heard earlier today, we're making huge progress in the launch arena. We're making investments in commercial crew transportation. The Sierra Nevada Dream Chaser program is a really cool program, using some green technologies instead of the toxic rocket propellants. So making great progress in various areas. SpaceX is here. We'll hear from them later. And the SLS, which Lori Garver talked about earlier, will enable the Orion capsule to go beyond low Earth orbit. And that's a great step. But we need to take more than just the Orion capsule, right? It'd be kind of boring if the only thing that you had was the Orion capsule there, and it's not all that big. So we also need to send food, water, habitats, rovers, ascent vehicles, all of that stuff that is needed to do those interesting missions that we want to do in an affordable manner. And affordability is really central to, it needs to be central to the way that we think about deep space exploration. We need to think about cargo, not just crew. Much as the human part of a mission is what excites us all, if we don't have useful tools for them to use, and food to eat, and oxygen to breathe, and the rockets to bring them back, it's not going to be an interesting mission. So if we separate cargo and crew in that manner, our studies show that you can really dramatically reduce the cost of deep space exploration because you can optimize the two transportation systems. You can do crew fast, the way crews will want to go to Mars or back to the moon or to asteroids or wherever they end up going. And cargo can be pre-positioned. And it's really the same analogy, the way we do it on Earth right now. We don't have one transportation system. We heard about aircraft earlier. But we also have big cargo ships, and we have trains. And so the way that we think about transportation architectures really needs to move from the way we're currently thinking about deep exploration to a new paradigm if we are going to truly get the cost of deep space explorations down. The cool thing is that the basic technologies are pretty much there. We've been doing this for decades now, and we have a lot of the basic technologies. So if we started a program today using technologies that are very near to application, they're not ready yet, but they're very near to application, I think we can go to the moon, the asteroids, the Martian moons, and the surface of Mars, and do it affordably. Specifically, if we use a combination of commercial crew, the SLS, the MPCV, modular cryogenic stages for crew transport, so those are the elements of the crew transport, and we use realistic high-power solar electric propulsion for pre-positioning cargo at our destinations, I think we can implement an affordable, robust transportation system for space exploration. And when I say transportation system, this isn't just to go to Mars. This is a system that would be multifunctional, go to all the destinations. It's another way that you get the cost down, is that you have systems which are used for multiple purposes by multiple markets. It's a very important way to distribute fixed costs, for example. So technologically, this seems doable, and it seems affordable to us if we do it right. But we have programmatic challenges, and this is the second part. So our biggest programmatic challenge is sustaining a technology program that sees new developments through to application. We have a lot of basic technologies. The electric propulsion systems have been around for a long time. Cryogenic rockets have been around for a long time. There are some new innovations that we need in long-term cryostorage, high-power solar arrays, very high-power solar arrays. There's some new technologies like that we do need. But pretty much, we're pretty much there from a basic technology perspective. Solar arrays exist today. Cryogenic rockets exist today. They need to be engineered. But it's not new technology, so to speak. But what we have not done is validated them. We have not transitioned them, and Lori Garver talked earlier today about transitioning technology. And it's an expensive process, but making sure that we can actually use the technologies with the appropriate risk profile is really what I'm talking about when I say transition technologies to application. And we don't have a robust program now for technology transition. I personally transitioned a lot of technologies in the commercial sector to space flight, several different propulsion systems, including some electric propulsion systems. But we need to take that next step with the larger missions larger systems that are required for human space exploration. So in summary, a lot of the technologies are there. We do need some key innovations, as I mentioned, but what we're lacking more than anything is a robust transition to application program, a sustained effort to take the technologies that we have and make them useful, show that we can use them. And I'll leave it at that for now.
Thanks very much for your thoughts, Roger. I'd like to now introduce, last but definitely not least, Dr. Ed Lazowska. Ed has the fantastic title of Bill and Melinda Gates Chair in Computer Science and Engineering at the University of Washington. And when I hear that title, I can't help but think that this person has the opportunity to really think big thoughts and think about the role of computers and information technologies and society as a whole. And that, in fact, is what Ed has dedicated himself to doing. He does a variety of things, both locally here and across the country, including directing the University of Washington's eScience Institute, which is the organization that tries to spread computing technologies across the UW campus. He chairs the Computing Community Consortium, which is looking at addressing challenges in information technology across the 21st century. And he also has been involved in the President's Council of Advisors on Science and Technology, addressing a working group there, helping to chair a working group there on reviewing federal networking and information technology research and development. So Ed is your person. Number one, if your iPhone has crashed, I think Ed is the guy to talk to help get that resolved. But really, Ed is the guy who's forecasting where we're going to be in the middle of the 21st century, at the end of the 21st century, for information technology, and that is a wonderful space to be in. So welcome, Ed, and we look forward to your comments.
Well, thanks. It's great to be here. That's, of course, an introduction that one cannot possibly fulfill, but I will say that almost everything has been said, so I'll at least attempt to repeat it quickly here. It's important that computer science, information technology is represented here today because really the two pillars of the technology economy in the Puget Sound region are aerospace and computing information technology. And this is a region that's really contributed to making our nation a leader in both of those areas. Let me tie the two together by going back to 1969. You've heard about Neil Armstrong and walking on the moon in 1969. There are a set of other important things that happened about 40 years ago in 1969. The Mets won the World Series. There was Woodstock. And more germane than either of those, and no one remembers what happened at Woodstock anyway, is that the first packet of data flowed over ARPANET, the precursor to today's internet. All right, so that happened in October, just a couple of months after an American walked on the surface of the moon. I'll give you a bit of detail on this because I'll come back to it later. The goal of ARPANET at that point was making it possible to remotely use expensive mainframe computers. Right? And the first packet that flowed over ARPANET was the characters L and O, which were the first two letters of the word login. Right? So a gentleman at UCLA was trying to log in remotely to a computer at SRI, and after he got to L and O, the network crashed. So there are a set of things that never change. Right? But these were both monumental engineering accomplishments that over time have changed our world. And most importantly, and NASA is really the poster child for this, they led to a set of aspirations that kids have and people have for what we can achieve, and mechanisms for fulfilling those aspirations. And that's what's so important about the space program, and I think so important about information technology as well. That is, it causes us to aspire to do things, to dream about what's possible. Now, computing has an advantage over aerospace and space travel, and that is that we benefit from exponentials. So you're familiar with Moore's law. If you go back just 20 years, all right, to 1991, the Intel 486 processor had 1 million transistors. And today's high-end Intel processors have 2 billion transistors, so a factor of 1,000 greater in 20 years. And the number doesn't matter. What matters is that it transforms what you can actually do. Right? Similarly, 20 years ago in 1991, there were about 500,000 users on the internet. That's a lot, but today there are about 1 billion. So again, a factor of 20 increase, and you get what we call network effects, right? Network effects are that the value of something increases exponentially with the number of people participating in it. So examples of these exponentials, in addition to transistor count and the internet use, is that I'm told that the computational power that was used to get Apollo spacecraft 20 years ago to make them successful is now embodied in a Furby. All right. So it's not clear that this is the greatest social use for that technology, but it's still a remarkable comment on what we've been able to do. So let me talk about what's happened in the past 10 years, what's going to happen in the next 10 years, and then how it happens. So, if you think about things that are totally different today than they were 10 years ago, you've heard already today about digital media. You've heard about mobility, the fact that you're connected to the world no matter where you are by a little device in your pocket. You've heard about social networking. We are using it today via Twitter and other means in this meeting. But there's search. 10 years ago, you filed things away so that you could maybe or maybe not find them, and today you just search for them. Scalability, e-commerce, the cloud, all of these are total revolutions in the past 10 years. Looking forward, I think the real contribution that we're going to help make in partnership with NASA and folks like Christie is putting the smarts in everything. Right? So that's the business computing is in. So when you hear about smart homes or smart cars or smart bodies, I always wonder why my body is so much worse instrumented than my car. right? When I go to the automobile dealership, they jack a little computer in under the dashboard, read out the parameters from the past 6 months, figure out what the problem was, and fix it. And when I go into the doctor, she taps me on the knee and sees if it bounces up and asks where it hurts, all right? And you got to believe there's something that will happen there. You've heard a lot about robotics. NASA has been a leader in robotics, and robots, in some sense, with the exception of NASA, over the past 40 years, have been in what we call structured environments, bolted to factory floors. And NASA has been a pioneer in robots in unstructured environments where they have to be autonomous and they have to respond to unanticipated situations. You see these in your home today in the person of the Roomba vacuum cleaner. You see Google's robot cars on the roads of California, right? And so this notion of robots in unstructured environments working with us is going to be transforming over the next 10 years. You're going to see smart crowds, citizen science, work done here at the University of Washington in this program called Folded. Has hundreds of thousands of people doing protein folding and protein structure calculation as a game. They were in the news a couple of weeks ago for solving an AIDS-related protein structure problem that had eluded scientists for a decade. And the beauty there is not that just that you're bringing many people to bear on a problem, it's that each of us has unique capabilities, unique strengths, unique things that we can do. And if you can design systems that let people work together, then you can really do something that no collection of identical individuals, much less a single individual, can do. So let me say just a word about how this happens. And again, I think there's a lot of commonality between computing and aerospace. There have been a lot of studies about how innovation takes place in computer science. And most importantly, essentially all of the billion-dollar subsectors of today's computing industry trace their roots to federally sponsored research. So the federal government has a really essential role in doing this, and it's a complex ecosystem that involves federal agencies doing research, federal agencies funding research, the university community, and industry R&D, and there's no simple pipeline. People and ideas are constantly moving back and forth. It really is an ecology that allows us to be a leader, and we have to maintain that ecology going forward. The interaction of research ideas multiplies the effect. There's an unpredictable period from sort of first idea to billion-dollar market. And most interestingly, it's often not clear at the outset what the real benefit of an innovation is going to be. When people were working on the internet, ARPANET, nobody was thinking about email or the web or e-commerce or digital media. It was for remotely using expensive mainframe computers. So, you see this pattern again and again. The final thing I want to touch on is the role of universities in tech transfer. This is something that's commonly misunderstood. And I think it gets back to this ecosystem notion. The goal of university technology transfer is to put publicly funded innovation to work for the public good, right? And people have to get over the notion that somehow you're going to float the institutional boat on licensing revenues and realize that the goal is to make our nation the world leader and make our regions regions of innovation. So there are very many ways in which universities contribute to innovation. Explicit technology transfer via licensing is just one of them, and by no means the most important. It just gets the most attention. So the bottom line message here is it's an ecosystem. We have a wonderful one in this region. We have a wonderful one in this nation. It's up to all of us to preserve it and to make sure that the next generation appreciates the wonder of discovery that we've been fortunate enough to participate in. Thanks very much.
Wonderful. Thank you so much, Ed. Those were really insightful remarks. So what I'd like to do now is open the floor to questions. And while folks are coming to the microphone, we're receiving questions from Twitter as we go along. And we received one from Matt Moffat on Twitter, who asked about space applications for robotic nanotechnology. So he's interested in the tiny robots. And I was wondering if perhaps Christy might want to take a crack at that, or someone else on the panel, to talk a little bit about space applications for robotic nanotechnology.
Sure, I'm happy to start, although I will say I'm not an expert in nanotechnology. I tend to work on a slightly larger scale than that. So What I can say about it, there's a number of things going on. So there are projects called CubeSats that are being worked on by a number of people. So those are not nanotechnology. They're, I'm actually not sure of the exact dimensions, but they're usually, bread box size.
Yeah, 2 or 3 kilograms.
10 centimeters.
10 centimeters, okay. So that's one area. I think some of the limits with going smaller than that in space applications are, what are you trying to do? So if you have actuation limits, so you need to have enough power to move or actually accomplish something in terms of manipulating the environment, they tend to need to be a larger scale. So achievements in that area, like I said, there's the CubeSats. There are also a number of things going on in air environments in the Earth, so small flying things. And people are also looking at getting medical robotics inside of people on that scale as well. So, maybe.
I could comment on the applications of robotics and the kinds of things that I was talking about, pre-positioning cargo and putting habitats in place and maybe starting in situ propellant production. Those kinds of things will require highly autonomous systems, robots, to go do those things. And so I think it's an essential piece of an affordable space exploration program. I think, as Ed was saying, computer science is absolutely integral to everything that we're going to try to do.
Great. Thanks very much. I must say that I've envisioned many questions that I'd like to ask of Bill Nye, the science guy, but I never imagined that we might be taking a question from Bill Nye, the science guy. So, in a bit of a role reversal, please, Bill.
How much are you all working on what I'm going to call biofuels? These would be renewable fuels. And it seems to me, not just, I'd like to know what NASA's doing. I'd like to know what distributed computers doing. And I'm very interested to hear what the Museum of Flight, if there's any plans to have a renewable fuel display here. I'm imagining algae that's been genetically modified to produce kerosene or something akin to that versus swamp gas. And then in closing, I have another question about efficiency. Is there really a good reason that door is open? I'm not kidding. It seems I feel cold air coming in. I see natural light, which of course is unsettling. And I hear a lot of noise that you guys have to overcome. So this to me, I think if I understand it, biofuels would be part of the future for national security reasons, but also for this fundamental bigger idea, especially in space exploration, we have to do more with less. So I'm looking forward to hearing your answers.
Thanks, Bill. Bob, please take a crack at the discussion on biofuels.
Yeah, I'm not sure I can answer the door issue, but on the at least on the aviation side, so NASA is working in partnership with DoD, FAA, and industry on the overall life cycle issues associated with biofuels. So the piece that we're working on, that NASA's working on, is the characterization of those fuels in the engines, in the systems, and so forth. So others are working more of the development of the fuels themselves and the especially the DOE and so forth, and the scaling of those and the production. But one of the key issues in aviation is you got to be able to drop, basically we call it drop-in fuels. You got to be able to drop the fuel, and you got to be able to use current systems. So we have to characterize, make sure that all the seals, are going to keep their integrity. That the other aspects of emissions are well characterized. That we get the same level of performance and so forth. So we are in a really tight partnership with the other government agencies and industry in doing that, and a lot of progress is being made. We've had a couple of campaigns already, ground campaigns, where we put it onto a couple of vehicles that we have. We've done this out at the Dryden Rice Flight Research Center, and basically looked at what's coming out the tailpipe. We haven't done it yet, but we are looking at doing a flight campaign as well. So actually taking up flying these, and then having other aircraft in trail, collecting the exhaust so that we can measure it in flight as well. So we're quite active in that arena.
From a space exploration perspective, it's a fascinating question. I'm not aware of any particular work that's directly asking that question, other than some interesting work on the potential for growing plants and algae, for example, that would be used to make fuels on Mars. And there are some very early preliminary studies being done to ask, how would you set up a greenhouse on Mars that might enable, for example, the in situ production of some of those fuels, for example. That certainly hasn't been the focus. It's been food and oxygen has been the focus so far from an exploration perspective. But I would imagine that we'll be leveraging what the aircraft industry does in that case.
Great. Thanks, Roger.
Let's take some more questions.
Okay.
Reese Lumsden, space enthusiast. My question kind of is predicated on your earlier comments, Joe, and actually it's for the whole panel, however. I kind of find it a little bit ironic that when we talk about NASA and what's held up as the kind of strategic element of NASA being the space shuttle, as I'm sure most of you on the panel know, but probably most people don't know, is predicated on 1960s and 70s design, 80s technology. So it's kind of ironic, obviously, that we're talking about innovation and technological advancement, and yet the centerpiece of NASA was the space shuttle, which is obviously very old technology. But I think it gets into what you were talking about, Dr. Myers, about how incredibly long it takes to have hardware in space. And I think that kind of hints at where we perhaps need to broaden our definition of innovation, not just to focus on technology, but also those things that enable technology. I would suggest, and I'm sure most of the panelists here have probably heard this argument time and time again, that if we were to see innovation in our export control and regulatory regime, that would immensely expand and forward our space economy, in inverted commas, because I guess we don't really have a space economy. But it kind of also hints on something that also all the panelists, I'm sure, are aware of, this idea of tech push versus need pull. Jump across to the pharmaceuticals industry and you see that there's certainly a lot of money the pharmaceuticals are pushing into drugs for diabetes, drugs for heart disease, and dare I say it, drugs for male impotence. Why do they do that? It's because there's an increasingly never-present need for it from the market basis. And so I guess my question after all that is, how are we going to balance tech push versus a market pull when, for space, we don't really have a market? I would suggest that if we suddenly found a colony on Mars, we would see launch system development increase, or certainly the money to go to launch system development increase rather rapidly.
Thanks. One quick remark. Sometimes I'm approached by people who ask me why NASA is covering up evidence of life on Mars. And I'm fascinated by that question, because if we were to find life on Mars, what would that do to NASA's budget? It would skyrocket. And so if there's life there, we're very interested in finding it, and we're very interested in getting the word out. So innovation is a fascinating thing. You mentioned this notion that the space shuttle is actually taking advantage of 60s and 70s technology, and yet it's held up as one of the great technological achievements of recent time. One of the reasons why we're not in a position today to send humans beyond the moon and onto asteroids and Mars is we don't actually have the technologies in hand to accomplish that. And so what we're doing at NASA now is trying to develop the technologies to enable these incredible missions. So today's technologies become tomorrow's missions, and the real question is, how do you shorten that life cycle so that you're not having to wait 20 years from the advent of a technology to when it can actually be implemented? That is a huge challenge that we're trying to face. I wonder if any of my colleagues would like to talk about this interplay between push and pull in technology. And once we do that, we'll go to our next question. And we have about another 10 minutes, and I see several people waiting in line, so I'd really love to be able to get to all of your questions if we can. Go ahead.
Well, so I can say something about the technology push and pull. I mean, I think it's something, I don't think that there's an algorithm that we have for optimizing that right now, but I think it's something that you don't want to suppress either side of it. I think that there needs to be the driving questions from the funding agencies that say, we definitely want people looking at these particular problems to solve, but you also need to be engaging the general population in terms of what do they want, and make sure that they're aware of the latest innovations, and then just see where they take them, because I think you just don't have any way of necessarily predicting, and you shouldn't. So I don't know that there's a fixed answer to that, other than we need to have activity on both sides and actively engage it.
Great. Thanks.
Dave Anderson, retired Boeing product development. Mine is an easy question. I believe there are still discoveries to be developed that benefit commercial air transportation. My interest primarily is in aeronautics, but I know that can be linked to space exploration and even underwater exploration. NASA has had an interest in understanding the physics of flying through atmospheres other than Earth's, so that when we get there, we can move fast. Can you tell us about that interest and progress?
Let me take a crack at that. First of all, let me confess to my greatest life dream is to pilot an aircraft in the atmosphere of Mars. That would, for me, be completely fulfilling. So I've been looking at this technical challenge. We've approached it from a couple of different perspectives at NASA with mission concepts, some of which are looking at flying in very rarefied atmospheres like the one we have in Mars. The Mars atmosphere at the surface of Mars is roughly equivalent to 100,000 feet at Earth. So you can imagine aircraft flying on Mars that look like our very high altitude aircraft like the U-2, or might perhaps look more like rockets that are not depending on lifting surfaces to achieve their flight. We're also looking at operations in atmospheres other places, like in Titan, the moon of Saturn, and it has a fascinating atmosphere that's much more dense than the one I just mentioned at Mars. And it turns out that balloons are one of the more optimal systems for exploring around Titan to find some perhaps biological precursors for life that we've only found as organic compounds, or evidence of organic compounds now, and we're wondering what might be there next. So aerial atmospheric flight in planetary exploration is a very rich research area at NASA, and we're looking to take the next steps in actual mission concepts for how we might execute some of those missions in the future.
Thank you.
Ryan Lobsher, Odysseus Technologies. Roger Myers outlined all the technologies that are available for in-space propulsion. But what about the hard part, which is from the surface of the Earth to low Earth orbit? So my question to the panel is, what do you think the next new paradigm for propulsion from the surface of the Earth to low Earth orbit is going to be?
Roger, would you take that?
Sure. When you say new paradigm, I mean that we've done studies of beamed power launches, we've done air launch. In fact, Virgin Galactic's going to do air launch. There are various different architectures. I hesitate to say, it's the next new paradigm. One of the messages I tried to convey is that it takes a long time to transition technologies, and if we look at what SpaceX, for example, has done, they have dramatically reduced the cost of launch by focusing on how to build less complex vehicles. And so they didn't, you could say, they went to old technology, but look at the cost reduction that they have enabled by actually, in some sense, using older technology and focusing instead on the manufacturing flow and the way that they build their systems. So it's hard to predict what the next new paradigm is going to be. I know there's a program that the Office of the Chief Technologist is funding now on Ride the Light. It's a beamed power system, and actually we're doing one of those studies. Frankly, the state of the art of laser technology, even looking out 10 or 20 years, makes me personally concerned about the real feasibility of that architecture. So I'm not sure that we're going to see huge differences in terms of a paradigm shift in launch technology, just given the reality of how much energy it does take. I will say that I do take some exception to your characterization of launch as the hard part. Look at the total mission and the energy balance of the whole mission, and you will find that actually you need to do both. You can't say that one is necessarily harder than the other. We're focused on launch now with the commercial crew and the COTS programs that we heard about before and the SLS, because that's where we are. But if we want to go beyond LEO, look at the total energy, and you will see you need to do both. A very effective job at getting affordable systems in both areas.
Thanks, Roger. We have about 5 minutes left, and I'd like to sort of go to the lightning round of questions and answers. So if you could be as succinct as possible, and we'll try to do the same.
I'll do my best. Meredith Anderson, flight test at Boeing. The panel mentioned two technologies, blended wing body and pilot on the ground technologies, that the technological side exists, but there's a human factor challenge. And that's really hard for industry to break through. Is there any sort of national, international, social networking campaign to help with the human perception side of things?
Yes, so let's see, lightning round. You're absolutely right, big issue. The history has been, for a new configuration like that, we look to try to partner with the military, with the DoD, to see if they've got a mission that works, mature it there, and then transition it to the civil sector. And honestly, for things like hybrid wing body and things like that, I see the same. I think we got to look there. We got to see if we can make that work with the military, because that's the best way to get these things in full scale and get them out and then get some experience and then transition them to the civil sector.
Thanks.
Yeah, my name is Bruce Pittman from NASA Ames. I guess the question I'd like to ask is, following up on Lori Garver's comments about the difficulty of bringing new technology in the battle between the past and the future in aerospace. And I guess my question for the panel is, why has it been easier to do that in other industries like personal computers and software, and so much more difficult in aerospace to make these technological advancements and evolve the technology? And is there anything that we can do about it to enhance that?
Two words, Bruce: risk tolerance.
My name. I would also say profit motive. Right on point for me. My name is Gene McBrayer. I'm a trustee of the Museum of Flight, a private pilot, and an experimental aircraft builder. So I can identify with Joseph about that and his brother. I'm also interested, have been my entire career, in economic energy solutions, underscore economic. And I'm impressed with how uneconomic many of our forward-looking solutions are today. I'd like to ask you about some technology that I know NASA developed at least a decade ago, the concept of putting in geostationary orbit around the equator arrays of photovoltaic cells, where it maximizes the efficiency of the photovoltaics we have today and beams it back to Earth with demonstrated microwave technology. The studies I saw said that the physics is clearly there, the efficiencies are there, except for one thing: the economies of putting that much material in space to create those arrays. When are we going to get Moore's Law to work on that? If we could solve that problem, I honestly believe we have a long-range energy solution that would produce enough electricity to replace all of the other options by the 21st century. What are your comments on that?
Well, one of the things that I would say is that putting things in geosynchronous orbit takes twice the typical spacecraft that is launched to geosynchronous orbit is half propellant. And that's if you launch into geosynchronous transfer orbit. If you launch to low Earth orbit, which is the lowest cost place to launch to, it's even more. So you're launching mostly fuel, which does not make power, right? It doesn't create revenue. And so one of the things that we really have to do is invest in systems, and I'm sorry, but in-space propulsion systems, to get the total mass that you have to get to low Earth orbit down to the point where you're not paying for these enormous, unique rockets in order to get those space power systems to GEO. If you can shrink the architecture, make it more affordable, use rockets that aren't unique to that one application, but instead the DoD might use, commercial industry, and then they launch ComSats. If you can distribute those fixed costs, now we're talking about really changing the economics of space travel. And that's kind of exciting to me personally.
Great.
Sorry, that was not a lightning round.
I think we have time for just one more question.
Lloyd McCracken, and a question on manned space flight. We've been in low Earth orbit, and we've experienced long periods of time up there, but the big challenge to go to the moon, Mars, anything, is getting outside of the protective envelope of the Earth. Once we get outside that, we're exposed to radiation and the human factor. We can send robots all day long. It's the human factor. How are we working on shielding to really protect humans to be able to actually venture outside low Earth orbit?
Thank you for raising that, because it is actually ironic that when I talk with my colleagues at the Johnson Space Center in Houston and ask them what do they think are the biggest technological challenges to going beyond the moon, they talk about radiation and they talk about psychology. Group psychology on these extremely long missions could be one of the biggest challenges that we face. But let me come back to the point of radiation and talk about some fascinating new technologies that we're looking at. One method of shielding for radiation is to put large, heavy things in between you and what you're afraid of. That might be water, that might be lead. It depends on the style of the threat. One thing that we're looking at NASA is making magnetospheric spheres, shields, if you will, that weigh nothing and require only power to achieve, that help to block radiation coming in that would be a risk to the crew and to the avionics on a spacecraft. And this is one of the ideas that has come through our NIAC program, NASA Institute for Advanced Concepts, NASA Innovative Advanced Concepts now is the name of the program. And we're looking at these really advanced ideas for trying to address issues like radiation. And I think that we may have some breakthroughs on this in the next 10 years or so, but it's at very low technology readiness right now, and we've only come to really appreciate the challenge that we're facing, not solving this problem with heavy, massive things, but much cleverer ideas that achieve the same end. So I think that brings our panel discussion on innovation to a conclusion. I'd really like to thank my colleagues Bob, Christy, Roger, Ed for their very insightful comments, and thank you, the audience, for your wonderful thoughts and ideas, and please keep the discussion going, and let's keep paving our way to a better future. Thank you.
Thank you, Joe, and our panel. That was great.